Hi everyone, welcome to today's video. In this session, we're going to explore a crucial data structure in computer science, the red-black tree. It plays a key role in many algorithms and systems, and it's widely used in real-world applications. Today, we'll break down why red-black trees are needed, what makes them special, and where they are commonly used. Before we dive in, let's talk about why red-black trees were introduced in the first place. You might already be familiar with binary search trees, BSTs, a powerful way to store and search for data efficiently. However, there's a catch. A BST can become highly unbalanced. In the worst case, it might degrade into something that looks more like a linked list than a tree. When that happens, search operations slow down from the ideal O log n time complexity to ON, which severely impacts performance. To solve this problem, we need a self-balancing binary search tree. One type of self-balancing BST you might have heard of is the AVL tree. AVL trees maintain a strict balance, meaning they keep their height as small as possible. Red-black trees work a bit differently. They are also self-balancing, but in a weaker or approximate way. Because of this, red-black trees require fewer adjustments when inserting or deleting nodes, making them more efficient in scenarios where these operations are frequent. That's why red-black trees are more commonly used in real-world applications. So, what exactly is a red-black tree? In simple terms, it's a binary search tree with an extra property. Each node has a color, either red or black. The tree follows a specific set of rules to ensure balance. There are 5 key rules that define a red-black tree, so let's go through them one by one. First, every node is either red or black. Second, the root node must always be black. Third, all leaf nodes must be black. Here, leaf nodes refer to special nil nodes, also called sentinel nodes. These are placeholders that don't actually store any data. Fourth, if a node is red, both of its children must be black. This rule ensures that 2 red nodes are never consecutive. Fifth, for every path from a node to its leaf nodes, the number of black nodes must be the same. Now, let's look at a specific red-black tree as an example. First, since it's a binary search tree, an in-order traversal of its nodes will produce a sorted sequence. But what makes it a red-black tree is that it follows all 5 rules. Let's verify them one by one. Every node is either red or black. Check. The root node is black. Check. All nil nodes are black. Check. Every red node has black children. Check. For example, node 8 is red, and both its children, 1 and 11, are black. Similarly, node 22 is red, and both its children are nil, which are also black. So this rule is satisfied as well. Finally, let's check the 5th rule. Every path from a node to any of its descendant nil nodes must have the same number of black nodes. This number is called the black height. The black height of a node is the number of black nodes along any path to a nil node, excluding the node itself. In our example, I've marked each node's black height in blue. The root node 13 has a black height of 2, meaning every path from 13 to a nil node contains exactly 2 black nodes. The red node 8 also has a black height of 2, while the black node 25 has a black height of 1. Since this condition holds for all nodes in the tree, the 5th rule is satisfied. In summary, this tree is a valid red-black tree. The 5 rules of a red-black tree guarantee that the longest path from the root to a leaf is at most twice as long as the shortest path. The longest path consists of alternating red and black nodes, while the shortest path consists of only black nodes. This means that while red-black trees aren't as strictly balanced as AVL trees, they still maintain a good enough balance, also called weak balance, which ensures efficient operations. One quick note. In future demonstrations, we won't explicitly show nil nodes to save space, but you can assume they're always there. Now, let's talk about the time complexity of key red-black tree operations. The main operations are search, insertion, and deletion. Searching works exactly like in a regular binary search tree, by comparing values and moving left or right until we find the target node. Because the height of a red-black tree is always O log n, the search operation also runs in O log n time. Insertion and deletion are a bit more complex because they can break one or more of the 5 red-black tree rules. To restore balance, we use 2 key techniques: recoloring and rotations. We'll explore these in detail in later videos. Even though these adjustments add some extra steps, the overall time complexity remains O log n, just like searching. Finally, let's talk about where red-black trees are used in real-world applications. Thanks to their self-balancing properties and efficient performance, they are widely used in software development. Many programming languages have built-in data structures based on red-black trees. For example, Java's TreeMap and TreeSet, as well as C++'s standard map and set, all use red-black trees under the hood. Operating systems also make use of red-black trees. In the Linux kernel, a red-black tree is used to manage virtual memory areas, VMAs, which helps optimize memory allocation and deallocation. Red-black trees also appear in some networking systems. For example, Linux's IP set may use red-black trees to store and quickly match IP rules. So, to sum it up, red-black trees are a highly efficient and widely used data structure. In our next videos, we'll dive deeper into how insertion and deletion work in a red-black tree, walking through the process step by step. See you next time.